this video is relaxing. I thought that we could just chill together, chit chat a little bit about projecting one vector onto another. It's just a random topic. I have my little whiteboard today, so we can just do a little show and tell on our whiteboard. And yeah, that's it. I hope that you can sit back, relax, fall asleep if you need to sleep. I hope it's interesting and helpful if you're actually learning this, but feel free to just zone in and out as you please. Play around with whatever concepts you want to do. Let the rest just wash around you. I thought this random kind of chit-chat style could be nice and relaxing to drift in and out with. So, there you go. So this is going to be an application of the dot product. So we're projecting one vector onto another. The main formula involves finding the dot product. So we've talked about that here in the past a little bit. So if you want to review some of this, I recommend that you check out the linear algebra playlist, and depending, sometimes this is introduced in pre-calculus too, like as a miscellaneous random topic. So I'll add it in that playlist as well, but browse around whatever level you want to do. Just we're jumping around, having fun. So just wanted to let you know and make sure that you're aware of those playlists, so in case you want to like review the dot product and stuff like that. But you know that math comes in layers, so we're always reviewing and playing around and practicing and repeating. So we'll probably mention the dot product again today. But so what we're going to do is talk about what it means to project one vector onto another. I'll introduce the formula, and maybe down the line we can do a particular, like an actual calculation, like an actual problem. But for now, I want to keep it kind of chit-chatty and relaxed and maybe boring or whatever. It's not boring to me. I think it's cool, but you know, just whatever. Don't worry about it. Don't stress yourself about it. There's no homework here. There are no tests here. Only the occasional cooperative pop quiz. Speaking of, if you haven't voted on your answer for the last one, we still don't have a majority on the correct answer, so please take a look at that. But anyway, let's take a look at projections, okay? So let's say we have two vectors, U and V. Those are just the typical, letters for this kind of stuff, but of course you can extrapolate to change whatever you want. And for now we're going to draw two-dimensional vectors, but this works for 2, 3, 4, dot, 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 dot. And as long as the two vectors are in the same dimension, right? Because otherwise you can't dot them. So two-dimensional for now, because we have this flat surface. That's totally okay. No specific examples right now, just kind of general idea. So let's say I have a vector here like this. It's an arrow. It looks like an arrow. It is an arrow, I guess. But vectors are basically these objects that have a length called the magnitude and a direction. So this thing is pointing that way and it's of this length. So this actually is the distance. So the edge of the arrow matters, okay? So it's not like I'm just pointing this direction and so the vector, like here's a different vector. If I extended this, it's a different vector, but it's a different vector in the same direction. So that's why I kind of have to be careful with the word arrow, but it looks like an arrow and it basically is an arrow. Just note that the actual length of the arrow matters as well to define a vector. It's not just the direction that it's pointing in, okay? So this is my vector u. I have a little half arrow up there to show you that u is a vector. Let's say I have another vector v, and I'm going to point that, let's say, like this, okay? So this is a smaller magnitude. It's shorter than this one, and this one's pointing this way, and this one's kind of pointing at a slight slant. It doesn't have to be too precise right now, but you see, we have two vectors, okay? So we're going to project U onto V. So the first thing I should note is right now we're not using specific numbers or coordinates, but in general you can represent vectors. Like in this two-dimensional case, we can represent it as something like, let's say 4 comma 4, like this. This is an example of the notation you might see. So this means, with the pointy brackets, means I'm going to draw an XY Cartesian coordinate plane and draw the arrow or the vector from 0, 0, which is the origin, to the point 4, 4. So 4 comma 4 is a point, not just a dot, a point in the Cartesian coordinate plane. So I'm going to draw from 0, 0 to 4, 4. That would be a vector, right? It points in that direction from 0, 0 to 4, 4. And so that would have a magnitude, which we can use the definition. So we could do square root of 4 squared plus 4 squared. It comes from the distance formula, with the special case that one of our points is 0, 0. And we can also theoretically use some trigonometry to get the direction, get some more information about the direction from 0, 0 to 4, 4. It involves right triangles. So just know that these two vectors can be represented in something like this on the two-dimensional case. So there is like a standard way to define these, but for now we're just sketching stuff out, okay? So what we're going to do is project U onto V. First thing that I'm actually going to do is copy and paste this V. Speaking of putting it into standard form, if this is my origin, I want to put this so that it lines up right there too, okay? Just so that it's not just two random vectors floating around. So I'm going to take this exact same direction, hopefully estimate the same length, so I'm going to just copy and paste it right here, like this. Okay, so I'm going to erase this V and put V right here. Okay, so that they are tush to tush, 0, 0. They would both, theoretically, if I were drawing it in standard form, this would be the origin, right? 0, 0. Okay, so now we have U and V. So what it means to project, it's kind of like intuitively, it kind of makes sense. You're putting a projector, like you can project this thing down onto V in a way. By definition, what it means is we are going to try to break U, my vector U, into two vectors. So it's going to be a sum of two other vectors. It's going to have two components. So U is going to have one component. We're going to call it W1. That's the most common, writing. The most common, I don't know what it's called. The most common way of writing and representing this, I guess. You might see different letters, but that's the general idea. You have one component plus another component equals this U. So that's what we mean by breaking it apart into two. We want the sum of the two components to equal U, and the way you add vectors is just the regular way you would, which is to create our parallelogram and do the diagonal. Don't worry if that doesn't make sense, but just know that this is the typical way of adding vectors. So we are looking for these two components. Now, W1 is going to be the component that is specifically parallel to V. So this is what it means to project U onto V. It's not just any two random components. One of them is going to be parallel to V. So it's W1 that is parallel to V, meaning somewhere in this direction or even this direction. So technically, if you have a negative number like negative V, it's pointing that way, it's still parallel. It's just negative of V. So basically a constant times my vector v. So w1 is going to be parallel, and w2 is going to be perpendicular to my vector v. So we want the two components. It's almost like creating your own new system, your own new coordinate system, kind of, right? So I'm going to kind of tilt this thing and make two that are perpendicular that add to this. So it's kind of like chopping off the part that goes anywhere off of this, if that makes sense. It's filling in a right triangle. So basically, looking at this picture using this U and this V, the projection is going to be basically like so. Okay, so it's this long vector here, that's W1, and then perpendicular to that, you're going to have a W2. And you can see that W1 plus W2, if I fill in that parallelogram, makes up U. Okay, so you can see W1. I don't know if this picture is clear, but this W1 is this entire vector. My original V was just this little one, but you can see they're all pointing in the same direction. So W1 is actually parallel to V, right? They're pointing in the same direction. So that's how I know that that's going to be W1. W2 is the one that is perpendicular to it, and we can calculate that after. So the W1 is the one that's actually what we call the projection. So we take this U and we project it onto that little vector V, which just basically squashes it down. But if we force this kind of down to this, we're not caring about the vertical part for the W1 part, okay? So it's squishing it onto a different plane, so to speak, and then we can calculate W2 from there by actually subtracting out once we find W1. So from this picture, U is W1 plus W2. So in other words, if I subtract W1 on both sides, I actually get that W2 is just going to be my original U minus W1. So we can actually calculate that after. But W1 is what we call the projection. So in short, we want the component that of U, like we're going to break U down into two components that are perpendicular to each other. To project U onto V, we want the component that is parallel to V. So it could go this way, it could go the other way, just whichever way adds up. It depends on the direction of U. So W1, again, is the component that is parallel to the vector V, and that's what we call the projection of U onto V. It's kind of like looking at the shadow of something, isn't it? What piece of it do we see onto this plane? So projecting U, so it's P-R-O-J, projection of U onto V. So I have a little subscript V like that, okay? So now there's a formula for finding this specifically. So what is the formula? This is the one that has to do with the dot product. So it's a little messy and a little scary to see at first, but do not worry. So I'm going to write it out. So I'm going to take my vector U, I'm going to dot it with V. Then I'm going to divide by the magnitude of V. Okay, and then I'm going to square that, which is actually quite nice. It works out well. And then I'm going to multiply that whole thing by V. Okay? Okay, so let's break this down. This is my projection of U onto V. It's U dot V divided by the magnitude of V squared, all times the vector V. So first of all, W1 should be a vector. The projection should be a vector. So how is this a vector? Well, U dot V, we said, is a number. It's a itself. So you just get the square root of each of the square root of each of the coordinates squared added together. So anyways, that's the magnitude. If you've seen vectors, you probably know this magnitude formula, but because we have a square root for the magnitude, then we square it, the square root goes away. So this is a number, that's a number, so the whole thing divided is going to be a number. This is a scalar. So this part of it is actually a number. C, we can just call it a C, but it doesn't matter. It could just be like 2/3 or whatever constant we have. It could be negative. Then that number times V. So V is our actual vector, right? The original vector that we're projecting onto. So it's going to have coordinates. So all that means is scalar multiplication. A scalar times a vector just means we get a new vector with each of the coordinates multiplied. So we're just kind of distributing that scalar. So we're going to multiply this thing by each of the coordinates in, or rather multiply each of the coordinates in V by this scalar to get our final vector. So that's why this is actually a vector to begin with, and it is parallel to V because it's a scalar times V, just by definition. So it's going to point in the same direction as V, but it's going to have a different magnitude, or could potentially, unless this is somehow the same thing. But we're not going to worry about the dot product being 0 because we're going to assume that they're not perpendicular, because otherwise that's redundant, right? You already have two vectors that are perpendicular. You don't need anything. There's no projection there, right? You don't need to even do that because we want the sums to work out. We want to be able to have two components, right? So we're not going to worry about 0, but everything else would just be a constant times V, okay? So, yeah, I'm pretty sure okay, that's it. I'm just trying to make sure I'm covering everything. So that's the main formula. U dot V divided by the magnitude of V, and then square that. So basically the square root goes away, all times the vector V. So then from there, that's our W1. Like we said, then once we get what that answer is, we have W2 is my original vector U minus this vector. So when you have a vector minus another vector, if they have the same dimensions, which these all will, you just subtract corresponding coordinates. So the x part, so you take the x part of U minus the x part of this mess, and then comma the y part of U minus the y part of this thing, and it should all work out. So that's it. So W2 is not the projection, it is just the part, the remaining part. It's the perpendicular vector. It's perpendicular to the projection. And so what you can do is, once you do all these calculations, I know it looks messy now, but the dot product is still just our multiplication, and then adding the bottom part is the square root goes away anyway because of the squared. So it's just the first coordinate squared plus the second coordinate squared. So it's going to probably be a fraction. Sometimes it works out nicely, but whatever that constant is multiplied by each coordinate of V to get a new vector. So that's a vector, this is a vector. So to check, that's the nice part about all this. Even if it gets really messy, you can always check to make sure you're on the right track. First of all, it should kind of look something like your picture, so you don't want like a vector like way over here and like down here. So you don't want something negative for this particular drawing. But sometimes you will, depending on what your vectors are, depending on what your U and your V are. But what you can do is add U or W1 and W2 together just to make sure that they add up to be U. So you add corresponding coordinates together, make sure you get your coordinates of U. Then you also want to make sure that everything is parallel and perpendicular as expected. So just double check again that it's a constant times V. We know W1 is parallel to V, but then you also want to double check that W2 is indeed perpendicular to W1. So once so if you dot W1 dot W2 with those numbers, just double check that that dot product is actually 0, because W1, W2 are perpendicular to each other. They should dot to equal 0. So that's just one way to check. And so if they add up to be U and they're perpendicular to each other, and you double check that this is indeed a scalar times my V to make sure that it's actually parallel to V, then we should have gotten the correct components. Okay, so I know right now it seems like kind of random, but if we have some nice numbers to work with, we can definitely sketch this out. It's going to be hard to do on a whiteboard like this, so I'll do it as a paper video, but I hope that this was kind of interesting. If you've learned it before, I hope that it's good review. The formula again is the projection of the first vector onto the second, so projection of U onto V is U dot 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 V, U dot V divided by the magnitude of V squared. That whole thing times V, the vector V. U dot V divided by the magnitude of V squared, all times the vector V. Okay, so if you are asleep,